Welcome back, everyone. Today's lecture is one of the turning points in the entire course. So, this will be the moment. The question, how did life begin, moves from philosophy and speculation into laboratory science. Everything we've seen so far, from myths to Aristotle to Pasteur, was setting the stage, but it's 20th century that finally gives us the chemical evolution, prebiotic chemistry, experimental synthesis of biomolecules, first protocells, RNA world, modern abiogenesis research. So, if the scientific revolution made biology mechanistic, the 20th century finally made it chemical. So, let's start with one of the most influential figures, the Oparin, Alexander Oparin. So there's the Oparin-Haldane Revolution in 1920s and 30s, and this is the work that Oparin put out, The Origin of Life, as you can see here, which you can find it online, and I will try to add as an attachment to here as well, which was eye-opening and really, really influential. There's an incredible work, incredible. So Oparin and Haldane are two thinkers working almost independently. Oparin in Moscow and Haldane in Cambridge, who never even met, yet created the first modern theory for life's origin spontaneously. The pro- question that's saying that life is a biochemical problem first comes from the Alexander Oparin. So, he was a biochemist who proposed that life arose gradually from a primordial soup of organic molecules at the time, and Haldane uh, suggested that the early Earth's ultraviolet radiation could power organic synthesis, turning Earth's ocean into a hot dilute soup. So they both came up with the primordial soup model. It's really poetic how parallel their thoughts are. Neither had experimental evidence, but they offered something revolutionary. Life emerged through natural chemical process and not through spontaneous generation or supernatural events. This is the first real abiogenesis hypothesis in scientific history. So Haldane actually once said he became biologist because there were too few gods left to disprove in physics and chemistry. If we continue with their model, but in this work, Oparin explains origin of life through step-by-step process of every molecule, which is really, really intriguing. It's a beautiful work. So their early Earth atmosphere model, which they introduced. Oparin and Haldane worked with geological knowledge of their time, and they assumed Earth's early atmosphere was strongly reducing, full of methane, ammonia, hydrogen, and water vapor. And is this important? Well, of course, because under reducing conditions, organic molecules form much more easily. No oxygen to destroy them, lots of hydrogen to build them. This atmosphere became the basis for all experimental origin of life simulations. He Oparin also introduced protocell model and membrane, and he created the conservates, which we will talk later as well, which is incredible because he almost predicted very, very accurately. So the primordial soup concept. So Oparin didn't stop with atmosphere. He proposed organic molecules formed and accumulated in warm ponds, volcanic pools, shallow oceans, and tidal flats, forming what we call the primordial soup. And then he did something visionary. He created the first protocell model. Coacervates. Coacervates are microscopic droplets that form spontaneously when organic molecules cluster in water. They have simple membranes, can absorb nutrition, can grow, can divide under agitation, contain internal chemistry. These were not alive, but they showed that compartmentalization, one of life's key features, can emerge naturally. This was the first step toward protocell research. So Oparin presented Kosarevat publicly by holding a flask and saying, "Behold, the ancestors of life." And people were shocked, and some scientists were really offended by that. But he had made his point. Lifelike structures can emerge naturally. So, Oparin and Haldane has incredible contributions. They introduced concepts that still drive origin of life research today, like chemical evolution, prebiotic synthesis, naturalistic origins, early laboratory models, and protocell precursors. Every modern abiogenesis experiment from Miller-Urey to Sutherland's RNA synthesis traces its intellectual origins to these thinkers. And if we go back to Miller and Urey experiment, we are jumping to 1953. This is an extraordinary moment. Stanley Miller, a 23-year-old graduate student in Harold Urey's lab, decides to test the Oparin-Haldane hypothesis. So they creates a closed glass system to mimic the early Earth. There's a water as an ocean, methane, ammonia in hydrogen atmosphere, highly reducing, as they put it, and he gives sparks um, as a lightning and condenser for rain cycle. And he runs this for a week and gets the result when he get the from here. And more than in the result, the water turns pink, then orange, and then red brown, and inside Miller finds amino acids, carboxylic acids, aldehydes, and simple organics, more than 20 biologically relevant compounds. This was the first experimental proof that life's building blocks form naturally under plausible early Earth conditions. It shocked the scientific community and became one of the most iconic experiments ever formed. Miller preserved the original vials. Decades later, scientists reanalyzed them with modern techniques and found even more amino acids than Miller originally reported, confirming how productive the experiment really was. So later, by the way, let's talk about at this. They generated many amino acids. So in all life on Earth, it contained only from the 20 amino acids. You can find it here. So this is actually a proof of evolutionary origin of ancestor, what we call Luca um, cell that ancestor to all life on Earth. The first cell we call living, called Luca. Um, so that cell had those 20 amino acids, and as life branched and spread, it changed a little bit uh, based on their ratio or levels, but it contained through the all life on Earth, which is one of the proofs that displays that we are all related. And Miller and Urey showed that those can be synthesized in those conditions very, very easily. But later there was revisions has been made since 1950s. Scientists tested many variations. Volcanic gas atmosphere produce more organics. A hydrogen-rich atmosphere give higher yields. Lightning simulations under early Earth conditions form complex organics. Hydrothermal vent systems generate peptides, and dry wet cycles produce polymers without enzymes. Because the dry wet cycles is also really interesting. It came from Wachhauser, if I'm not mistaken, and it displayed how polymerization in those molecules occur, which all these experiments were accumulate at this point. And some studies show organic can form under conditions far more realistic than Miller's original experiment, but Miller-Urey remains a symbolic beginning. So if we continue with, we're gonna show more philosophical side and deeply influential person, Erwin Schrödinger. In 1944, he published a book, a very tiny book called What is Life, which is a very, very, very influential and incredible work, and the father of quantum biology, and very interesting ideas on how mutations can be related to quantum, um, how electrons shifts, and in biophysics, how photosynthesis has been using these quantum systems as well and tunneling it. So he has very interesting ideas. So there was two revolutionary things. He proposed that life feeds on negative entropy, a beautiful way of saying life uses order to resist chaos because everything should follow the entropy, but life is not. And he introduced a negative entropy idea, which I would really advise go look for it if you a biology major or a physics major or chemistry. It's really, really good. But it's not related to astrobiology at this point. But I will continue. It can be related to origin of life and astrobiology. It make all life related to astrobiology. But the second idea, what he proposed that heredity is stored in a periodic crystal, a structure carrying genetic information. So he predicting DNA before anyone knew it existed or its structure. So Watson, Crick, Wilkins, Rosalind Franklin all cite this book as inspiration. This is a very incredible work. That a physicist, not a biologist, helped launch molecular biology. So Schrödinger actually gave his lectures in Dublin, um, and the rooms were so overcrowded that people stood outside windows to just hear his ideas. So this little book, What His Life Changed Biology, and very, very beautiful book. And let's follow. This is Rosalind Franklin and the first image of a chromosome here. We go through modern prebiotic chemistry. So today, origin of life research span dozens of chemistries and environments like volcanic gases, alkaline hydrothermal vents, hot springs, ultraviolet-driven synthesis, mineral catalysis, clays, ice, dry wet cycles, shock chemistry. The idea is simple life began through a network of chemical reactions occurring under diverse planetary conditions, and understanding those would even help us understand life in different planets astrobiologically or how they might originate and where to look for. So, origin of life is really a part of this astrobiology and the RNA world. We arrive at one of those powerful ideas in modern biology, the RNA world hypothesis. The RNA is a very strange and molecule, and it has very versions and incredible variety of functions. It can store informations, catalyze reactions, fold into enzymes we call ribozymes, and help proteins form with ribosomal RNA and transcriptome RNA, and in theory self-replicate. This means RNA could have been both the genome and metabolism of the first life, a dual function molecule which helped create this hypothesis that all might be originated from an RNA molecule. So evidence today is really strong, still very strong. There are arguments as well, but ribosomes discovered in 80s and RNA molecule evolved in vitro through selection, and prebiotic pathways for building RNA building blocks discovered by Sutherland. And RNA can catalyze peptide formation. rRNA at the heart of ribosomes show ancient catalytic role. The RNA world might not be the whole story, but it's really a major chapter and definitely played some role at some point. Right, but there are still challenges. So, what are the challenges of this idea? Fragile ribose, RNA hydrolyzes easily, and magnesium is both necessary and destructive at the same time. Polymerization is hard without any enzymes around, and nucleotides are complex to synthesize prebiotically, actually. So these challenges push scientists toward hybrid models like peptide RNA world because you need peptides for reactions and they can polymerize and they can synthesize prebiotically, has been shown, um, or lipid first, and we will go through them in the next slides. There were competing models. So metabolism first was introduced by Wachowser. Life began as a mineral-driven reactions around hydrothermal vents as a geochemical process, and then there was also uh, cycles. As you can see, these are autocatalytic cycles where every product um have produced a second product, and in time, with a chemical selection, they create a fabrication or production of these molecules as well, and these can be made in hydrothermal vents. And also at these vents there is an iron and sulfur world theory where vent systems these metals around them causing a gradient catalysis, a proton gradient where there can be electron exchange and metabolic cycles might have emerged. That's also another theory here. And there's also a lipid first theory, which fatty acids spontaneously form vesicles, protocells, and then compartments. This is a very strong idea because at the time of this recording, in 2025, there's a new paper has been published, and they displayed under the green light. I think it's the from, if I'm not mistaken, University of Harvard from the Cutler uh, a paper called "Self-Production as an Autonomous Process of Growth and Reorganization in Fully Abiotic Artificial and Synthetic Cells," where they displayed those fatty acids are capable of forming cell-like structures, heritability, and even divide by themselves. Very interesting. I will try to add that um, under this lecture as well. Hope it works. This is my first lecture, but let's continue. But before panspermia, did we miss anything? We should be. So peptide RNA world, small peptides and RNA can co-evolve and can solve instability issues. And in the systems chemistry, life arose from cooperating networks and not a single molecule, and all this have played their roles in production. And panspermia, um, this is very popular idea. It's not an origin story, but a transportation story. So there are different versions of it. For example, the lithopanspermia means life moves between planets on rocks like meteorites, and there are proofs of it. Many meteorites we find many organic molecules just around. And radiopanspermia, there's a spore-side particles pushed by starlight can live in the space, which is not proven. There could be cometary origins, common stellar prebiotic molecules, or a very science fiction idea, directed panspermia, that there are advanced civilization that seeds planets with life. While fun, panspermia pushes the problem elsewhere, but it does highlight something big. Life's building blocks exist elsewhere: comets, meteorites, interstellar clouds, and all that. The Murchison meteorite, yeah, that fell in Australia in the 60s, contained more than 70 amino acids and many not found on Earth, proving that space chemistry is incredibly rich, which was originated, if I'm not mistaken, by Mars. And Mars's historical background is very, very rich biologically. So, why all this matters for astrobiology? These 20th century breakthroughs opened the door to everything we study today: chemical evolution, organic molecules forming naturally, protocells can emerge without life, RNA has catalytic and genetic abilities. There are multiple pathways lead toward biology, and life may be a planetary level chemical process. This is the century where the origin of life becomes a scientific problem, not a metaphysical one. So, in this lecture, Lecture 5, we explored all that, and in the next lecture, we move into the age of modern astrobiology, the search for life beyond Earth, Mars missions, icy moons, extremophiles, and how our understanding of early Earth shaped our search strategies. Thank you so much for attending this lecture, and see you in lecture 6.